Hello. All right. Great. So I'm sure more people will keep joining. Um, let's see. So I was using this waiting list thing, and I'm not totally sure how this works, but hopefully new people who join will just skip the waiting room. I'm not sure. Well, we'll see. I'll figure it out. There's a lot of stuff about like Zoom and some of these, remote teaching resources that I'm still kind of learning. So, just bear with me. But yeah, welcome one and all to the first live Zoom, like sort of discussion section or something, whatever you want to call it, for Math 104. Oh yeah, okay. So people have to go through the waiting. I might just skip this waiting room thing in the future. Might not have been the best idea. I don't know. How do I just deactivate it? Very confusing. Okay, whatever. I'll figure it out. So today's meeting will probably be a little bit on the shorter side. Oh boy. Oh, this is a nightmare. All right. Oh, I can just disable the waiting room, it looks like. Yes. Good, good. Okay. Hopefully people will skip the waiting room now. Okay. So okay. Right. So what I was saying is, oh yeah, so it's gonna be a little bit shorter today. Normally what these are designed for, right, is it's gonna be kind of like a discussion section. So normally what I do in discussion sections is I kind of like give the class some problems to work on and then let you guys work on them, and then I go through the solutions, right? So I kind of want to do a similar thing in here, and what I'm going to try to do is have these always be oriented towards the problems that are relevant to the lecture for that day and similar to the ones on the homework, right? Similar, keyword similar, right? Now for today, the material is still relatively rudimentary. So there are a couple problems. We can do a couple problems with algebraic, rational and irrational algebraic numbers using the rational zeros theorem. So there are maybe two problems I had my eyes on that we could look at for that. It probably won't take super long. I'm also happy to answer any questions you guys have. I mean, in general, it's fine if you want to ask a question here about the material or anything related to the class, you can ask here. But I will remind you that there's also Piazza or email or whatever as those are alternatives if you want. Because I know the live setting can be a little bit, awkward or a little bit intimidating or whatever. So yeah, you don't have to, but definitely you're welcome to ask questions here. So with that, I guess actually I'll go ahead and sort of open the floor to anyone who might have a question. I think there's a hand raising feature. Hold on. I don't really know how the hand raising feature works. I don't know if I see it in the chat or something. I still have to figure that out. I guess for now, if you have a question right now, you can just unmute yourself and ask if you want. Does anyone have any questions?
I had a question.
So yeah?
You said that collaboration is encouraged, but is there a platform where we can talk with each other or is that
right? So when it comes to collaboration, what I would say is yeah, it's a little bit. I was kind of gonna. My intention was to kind of leave it up to you guys to get in touch with anyone you might want to collaborate with, I guess. But I realize that you guys probably don't know each other at all, so it might be kind of awkward. But maybe what I'll do is tomorrow. Let's say for tomorrow's meeting, similar to this one. I can figure out something, because Zoom has these like breakout rooms kind of, so I can do something where we can work on exercises, and I'll put you guys in like smaller groups, and maybe that will help, get people more interested in like being in touch with each other or something. Or I mean, if you have friends that are like, well, I don't know. Yeah. You can also try to use Piazza if you want. You could try to use Piazza for like soliciting collaboration or something. I would prefer it if people did not openly collaborate on Piazza. I might like take down posts. If people start like posting stuff on Piazza where they're like, oh yeah, this is my solution for this problem or something, like before it's due, before the homework's due, just posting their solutions and stuff. It might be a little bit dicey, depending, if you have questions about your own solutions that you'd like to ask on Piazza, that's perfectly fine. Like after the homework's due, then it'll be like very, kosher. You can also ask questions about the homeworks in office hours, but yeah, collaboration, I'm not sure, but I think maybe Piazza right now is like the best option for figuring out like who to collaborate with or something. Does that help?
Yeah, understood. Thank you.
Uh-huh. Other questions?
So, will the discussion ever be recorded, or if in the case we can't make a discussion, is there any other like way we can?
Yeah, they're all recorded. Everything's like recorded. Yeah.
Oh, I see. I see.
This is being recorded right now, just so everyone knows. Yeah.
I see.
Uh-huh.
I see.
Yep.
Thanks.
Yes, I also have a question. I wonder, in the syllabus, you mentioned that besides all the homework problem, we also have to answer the problem from the lecture.
Yes.
In the lecture, there are actually a lot of questions. So
right. Yeah.
Yeah. So like,
So,
which one do you have to answer?
Yeah. I figured this might be a little bit confusing. I'm sorry, it's confusing. Like this is just the best thing I could think of to make it you guys be responsible for watching the lectures. But basically, I in the lecture I'll always say like, this question you are responsible for putting on the homework, and I'll usually title it like, I'll say lecture 1 question 1. I'll write that out, right? So right now there's only one lecture question from the first lecture that you have to actually answer, okay? And when I introduced it, I said lecture 1 question 1, and I'll try to do that for all of them. So like it should be very clear which ones you have to answer on the homeworks and which ones are just there for you to like test yourself on, I guess. Yeah.
Okay, thank you.
Any other questions? Thank you. These are very good questions. Because I know it's like the format is like super confusing. I'm not sure I really designed everything in the best way. Maybe if you guys just want to type in the chat, just like so I can get a general, feeling. Like how do you guys find things so far? Like how do you find the B courses? How do you find the lectures, on YouTube and stuff? Like, is it okay? Is it like, I don't want this to be painful. So if you just want to maybe, well, I guess if you have any complaints, feel free to type in the chat or something. I won't take any offense to it, but yeah, as far as the lectures go, I already have tomorrow's lecture recorded. It's currently like processing in YouTube because I had to kind of like edit some of the stuff. So that should be up within like an hour or two, I think. No, I would say probably no more than 2 or 3 hours. 3 hours, absolute max, like no more than 3 hours. And the reason I try to lead like that is to give people as much time as possible to like watch the lecture before the day's discussion section, basically, right? Because these discussion sections are supposed to be about the lecture from like the same day. So I don't want it to be like super cramped, where you have to like watch the lecture and then like right before the discussion section or something. So I'm trying to get ahead with that a little bit. So yeah, you'll see the second lecture pretty soon, and I think it's hopefully not too long. It's a little bit longer than the first one. Definitely more parts, but they're kind of shorter on average. But I think it turned out pretty well overall. Let me think, is there anything else? that I wanted to say. Lectures. Yeah, that's all I can think of for now. For stuff for me to just, tell you guys. But so with that, let's see. Let me think about how to try to do this. Let me see how this works. I'm not sure. I'm not sure if I want to experiment with this yet. I think maybe what I'll do now, unless there are more questions, is we can just take a look at a couple problems. They're relatively straightforward, but couldn't hurt. And then we can call it a day. This will probably be a shorter day. So let's see. Let me share a whiteboard thing. So yeah. How about, so we'll just do this for now. So I do want to try using the breakout rooms in the future to let you guys kind of work with each other. Also, these problems are like kind of easy enough that it's probably, there's not a lot for you guys to like talk about anyway. But once we get into like more substantially difficult, interesting questions, I'll try to figure out how to use the breakout rooms thing to let you guys like get into small groups and talk to each other about stuff. But for now, what I'm going to do is I'm just going to write a couple problems down here, and I'll give you guys like, let's say 10 minutes to work on it. And then, so I'll just have the meeting running. I'll just like mute myself probably and turn off my camera. And you guys can work on the problem, and then I'll, come back, we'll resume, and I'll just explain the solutions basically, and you'll be free to ask questions, obviously. So yeah, let's just go ahead and do that. So I wanted to do just a couple problems about like algebraic numbers. Let me think. Yeah, let's do the stuff about algebraic numbers. So here's the first one. This is from the textbook. So some exercises. Whoa, this thing is finicky. Exercises from section 1.2. So this is 2.4 here. Show the cube root of 5 minus the square root of 3, all under the radical here, is not rational. And 2.7, let's see. I included one of these on the homework. Let me make sure I'm avoiding, well, okay. You know what? I don't care. If I give away the one on the homework, I don't remember if I put it on the homework. I might have taken it off last minute. Whatever, it doesn't matter. It's a simple question, so I don't care. Let's show that the square root of 4 plus 2 times the square root of 3 minus the square root of 3 is rational. Okay. So yeah, take about 10 minutes to work on that. And then when we resume, I will go through the solutions and we can discuss. All right, so yeah, I think we can go ahead and just talk about these now. And yeah, I'll say, like, in the future, well, yeah, basically, so it won't always be problems from the textbook. Sometimes I think sometimes I might just think of good exercises to do just kind of on my own. But yeah, there'll be like a good mix probably. I think it'll probably be more textbook problems than non-textbook problems, but some of them won't be. And yeah, in the future, like when the questions are more kind of interesting, I'll definitely be using I think the breakout room thing would be a good idea to let you guys like talk to each other. Oh, the one other thing I want to say before we continue is if you, I hate to plug this so much, but if you haven't done the scheduling poll, please do that at some point. It would just be super helpful to have like a comprehensive idea of when everyone's available, so I can schedule the office hours and I can schedule these meetings sort of once and for all and forget about it. Some of these might end up being in the mornings, which might be a little bit awkward, just because like it might be harder for some people to. I think what I might do is just have the Thursday ones be earlier, on the earlier side, because I noticed some people were available. Some of the people who weren't available at like 5 were available at like 11 a.m. or something like that. So I might have one every week, one out of the 4 every week be at like 11 a.m. So that's another reason why I want to make sure the lectures get posted like the evening before, so that if you do want to come to one of those morning ones, you have plenty of time to watch it. Okay, anyway, so let's go ahead and talk about these exercises here. So I'm gonna erase some stuff. Right. Okay. So let's show that this expression here is not a rational number. So the way it's, and I kind of explained another example of this in the lecture, but so the way you kind of do these things is, let's just for convenience set b equal to the cube root of 5 minus the square root of 3. Now you kind of just like undo the operations that are on this side, right? Just like in algebra. So we would say b cubed is 5 minus the square root of 3. And then if you sort of flip-flop, switcheroo things around, you'll get square root of 3 is 5 minus b cubed. And then if you square both sides, you'll get 3 is 5 minus b cubed squared. So in the end, we end up with 5 minus b cubed squared. Sorry, so this is kind of all, I don't know. Sorry. And then if you subtract 3, so now we have a polynomial over here, right? If you just distribute this out. So b is a root, oops, of the polynomial. Let's see, I wrote this down. Right, x to the 6th minus 10 b cubed plus 22 equals, well, yeah, anyway, so that's a polynomial. Sorry, dang it, this is an x. Okay, this is an x. Okay, anyway, right, so we have a polynomial here, 6th degree. So we know that b is a root of this polynomial, right? So now the key is to use the rational zeros theorem. So if you remember, or if you know how to use the rational zeros theorem, you'll see that the only rational roots, so the highest coefficient is 1, and the constant term is 22. So the numerator has to be a factor of the constant term. The denominator is a factor of the highest degree term. So that's just 1. So it's just the factors of 22 with plus or minus signs. So plus or minus 1, plus or minus 2, plus or minus 11, and plus or minus 22, I believe, are the only possible rational roots, right? And I'm not going to go through this, but if you just plug these all into the polynomial, you should find that none of them are roots. At least I'm guessing. And even if one of them is a root, then you just isolate that one and like specifically show that this number is not equal to it. But I'm pretty sure none of them are roots. I don't know if I've ever seen it work out where like one of these actually ends up being a root of the thing you get here. Because usually the thing that, like, by doing this, what we found is basically the minimal, yeah, there's like a higher theory to this actually, but this is basically the minimal polynomial for this number, as far as I can tell. I'm pretty sure, yeah, because the degrees are like relatively prime or something. So basically, this is the minimal polynomial. So it shouldn't actually have any rational roots. I'm pretty sure it won't have any rational roots. So none of these should work. But anyway, that's like a totally different, you don't have to know about that. Okay, I'm just trying to verify in my head without plugging this stuff in that none of these actually are roots. So yeah, don't worry, you don't have to know about that. So yeah, so none of them are. So that's it basically. That means, oops, that means, oh my God, I have to get used to this. That means that this number is not rational because it is a root and there are no rational roots. Okay. Are there any questions about that problem? I think it's pretty straightforward. Things are still pretty simple for now. So, but obviously, you know, there's no such thing as a bad question. I'm not trying to say that, you know, you shouldn't have questions about this. I want to be very clear about that. I remember people having questions about this last time. So anything? Okay. Well, in that case, let's go ahead and move on to the next one. And oh yeah, and the other thing I thought maybe is actually, let's just like clear everything. The other thing I thought I could do today maybe would just be another like example proof by induction. I might do like the formula like for the triangular numbers or something. It's one of the, yeah, it's a common like proof by induction thing. And if you guys have proof by induction questions, oh my God, my tablet stopped working. Okay, there we go. Yeah, so if you guys have proof by induction questions, that would be a good time to ask them. So let's do the next thing here. So we wanted to show, this is 2.7 now. Show that the square root of 4 plus 2 square root of 3 minus square root of 3 is rational. This is a little bit, maybe not like slightly trickier because I didn't really explain anything about this. Here's how I like to think about this, although there is like a sort of a cheaper solution here, but this is the way I do it. So if we imagine setting this equal to r, where r is some rational number, right? Then if you add square root of 3 to both sides, you'd get square root of 4 plus 2 square root of 3 is r plus square root of 3. And then if you square both sides, you'll get 4 plus 2 square root of 3 equals, and I'm going to write this in a little bit of a funny way, r squared plus 3 plus 2r square root of 3. Now, the reason I write it this way is because basically, if you look at, you know, this number, 4 plus 2 square root of 3, you can think of it as consisting of two parts, right? There's like an integer over here, or at least a rational number, right? There's like this rational part over here, and then there's a multiple of square root of 3. It's specifically 2 times square root of 3, right? So whenever you have like, so this number is basically of the same form, right? Like this is a rational number here, and then this is also rational. So what we have is a rational number plus a rational multiple of square root of 3 over here. And actually, it's a fact of algebra that whenever you have an equation like this rational number has to equal this one, and this rational number has to equal this one. So that tells us actually that r has to be 1 if this equation is true. And what's nice about that is that because this 2r has to equal 2, right? That's how I got r equals 1. So 2r equals 2. And then that actually checks out with this too, right? R squared plus 3 equals 4, which is what we want. To actually verify this, though, to actually verify that the original thing equals 1, what you might want to notice is just that 4 plus 2 square root of 3 equals 1 plus square root of 3 squared. So the square root of 4 plus 2 square root of 3 minus square root of 3 equals the square root of 1 plus square root of 3 squared minus square root of 3, which obviously is just 1. So it checks out, basically. Like, it's actually possible, I think, philosophically at least, it's possible that the number we get from this process might actually not be the value of the original expression. It's just like the only candidate value that could work, basically, right? Like, when I solve this equation, what I'm saying is r equals 1 is the only possible solution here, but I haven't actually shown that it is the solution. That's what this part does down here. That's just like being super pedantic and like crossing all my T's, dotting all my I's or whatever, right? So it's sort of like, once you get to this point, that's kind of like good enough. But anyway, that's the gist of, so basically the cheap solution here would just be to like kind of notice this off the bat, that 4 plus 2 square root of 3 equals 1 plus square root of 3 squared. But like, who's going to see that, right? So that's kind of why I did it this way. One kind of interesting thing, just a bit of trivia, but like the reason, what I was talking about up here, right? How like, you know, there's a rational part and then there's this like square root of 3, a rational multiple of square root of 3. The reason that these two parts have to be like separately equal to each other is basically the same fundamental reason that if you have like complex numbers, right? If you say like a plus bi equals c plus di, then a equals c and b equals d, right? They have to separately be equal, like the real and imaginary parts. It's actually algebraically, from an algebraic perspective, like this is the exact same principle up here. It's kind of cool, but I guess that's just like my interest in algebra kind of bleeding through, because I'm not actually, I am an algebraist by trade. So I know analysis, obviously, but it's not really my specialty. So yeah, anyway, so that's enough of that. Any questions about this?
Do you mind explaining again the arrow, right, that you're like right above?
Oh, this thing here?
Yeah,
Yeah,
you
so
got
all I did was I squared both sides. So square both.
Oh, I see. Okay, okay.
Yep.
Thanks.
Yep, no worries. Oh yeah. So yeah, I said I was writing it in a weird way and I didn't really elaborate, but yeah, like when you square this expression, I kind of like automatically FOILed it out or whatever, and then like separated the terms, right? So like the normal way to write this would be like r squared plus 2r squared of 3 plus 3, but I just kind of grouped them in this specific way to illustrate this thing that I was talking about. So thank you. That was actually a good question. Any other questions? Okay. So yeah, let's just like round it out. I'm just going to show you guys another proof by induction and give you a chance to ask questions about that if you need to. So here, let's do this. And I actually did not like specifically plan on this before, so apologies in advance if there are a couple bumps where I have to like think about what I'm doing, but there shouldn't be. It should be smooth. Let me actually look. Yeah. All right. So let's do prove by induction. This formula, famous formula for what are called the triangular numbers. So this is 1/2. Oh, whoop. Jesus. Why am I doing this stuff? n plus 1. Right, so this is otherwise known as n plus 1 choose 2, for the area of a triangle that's n dots tall and n plus, or yeah, I don't know, whatever. All right, I'm not going to get into it. Anyway, right, so let's just prove this by induction. So the base case, right, you always do that first. in this case, it's n equals, this is, for all n greater than or equal to 1, or, n in the natural numbers. So the base case is n equals 1. In that case, the equation is just 1 equals 1/2 1 times 1 plus 1, which checks out, right? So that's good. So now we formulate the inductive hypothesis, right? Suppose 2 plus equals 1/2 n for some particular n in the natural numbers. Okay, this is weak induction, by the way. So there's also strong induction where you actually suppose that this formula is true for all the natural numbers up to a certain number. And that's actually pretty useful. Like, we might actually be using that later. So I might upload a supplementary video about that or something, for anyone who isn't already familiar with it. It's not that much more difficult to understand than weak induction, I don't think. Yeah, it might be useful. But for now, we only need weak induction. So we're supposing this is true for some particular value of n, right? We already know it's true for at least one value of n. And what we're trying to show is that we can derive that it's true for the next value of n from whatever value of n we happen to be looking at. So that would mean basically, like, the fact that it's true from n equals 1, like for n equals 1, and the inductive step proof mean that it also has to be true for n equals 2, right? And then the fact that it's true for n equals 2 plus the inductive step means it's true for n equals 3. That's the idea behind proof by induction, right? So let's actually do the inductive step. So now we use this assumption. So the inductive hypothesis means then if we take this equation and just add n plus 1 to both sides, right? Sorry, the equation's getting kind of broken up in a weird way here, but so it'll be 1/2 n plus 1 plus n plus 1, okay? And now we can just like manipulate this until we get what we want. So if you factor out n plus 1, you'll get, or let's factor out, yeah, let's factor out n plus 1 actually. So you'll get n plus 1 times 1/2 n plus 1, right? Oh, and let's also factor out a half. Okay, dang it. I thought I had to do that before, and then I didn't believe myself for some reason. So we have n plus 1, and then we have n plus 2, right? Otherwise known as n plus 1 plus 1, right? So this is the equation we wanted. So this equation here, let me write this in another. I'm trying to get better at using like all the cool features, fancy features and stuff, right? So this and this equation is what we wanted to prove, right? Because this equation here is just the same thing as the general statement, or like the inductive hypothesis, but with n replaced with n plus 1, okay? So it's just another example of proof by induction. It's a very common technique, and it's generally, it sort of follows the same pattern pretty much every time. It just takes, because I taught Math 55 before, and that's a class where we actually introduced the concept of induction to a lot of people for the first time. And I just have these kind of like traumatic memories of like how difficult it was for people to grasp. It's sort of, because I mean, it's a difficult idea, okay? It really is, you have to like, like meditate on it or something. You have to be, do some kind of like, like ritual or who knows what to like internalize the understanding, the Tao of induction or something, right? Like you have to really you have to like grok it. But then once you get it, it's like not that bad, you know? So anyway, don't like, you'll get there if you just think about it enough. Okay, you have to believe in yourself. All right. Anyway, that's enough. And do you have any other questions? Anything? Speak now or forever hold your peace, or at least until tomorrow. Okay. Well, great. Then I think we'll call it a day. And like I said, the new lecture should be up soon. And hopefully I'll work out the schedule of like these discussion sections and everything, and that'll all be posted. Okay, see you guys tomorrow.
Thank you.
Mm-hmm.
Thank you.
Thank you. You.